Just for perspective, I'm going to focus mostly on the central business district, which is, let's see if I can get the mouse to work, in this rectangle situated right here. It's about 40 kilometers east of the epicenter over here in Darfield, and here's the fault rupture for reference down below this bright red line. Christchurch started out in the mid-1800s, and I'm going to try to give you some historical backdrop to give you a sense of how this might relate to communities in the western United States and Canada. I think there's actually a lot of things we have in common. This was the town layout in 1877, and this, in fact, encompasses the entire central business district today. And so the city of Christchurch has actually grown far out beyond the original boundaries of the town. And the town planners at the time, if you could follow my cursor, laid out a central square, and in that they proposed in 1850 to build a monumental stone cathedral, and they called that square Cathedral Square, and I'll talk a little bit about that building as we go along. So the Anglican Cathedral was completed in 1881. It took 31 years to complete this building, and within a month after its completion, there was an earthquake in 1881 which damaged the spire. There was another earthquake in 1888, and the spire was once again damaged and repaired, and then again in 1901. Well, after 1901, they figured, well, for the third time, perhaps they ought to revise the design, and so they decided at that point to replace the stone spire with a wooden timber spire with copper cladding, which I think in hindsight was a very good decision. This is the way the church looks in 2010, largely unscathed. There actually was a lot of other seismic work done over the years on this building and many other monumental stone buildings in Christchurch. So I think it really serves as an emblem for Christchurch to show that they've made progress. They made a critical decision, 109 years ago, to make some substantial changes that affected the architecture of this building. Purists will tell you can't have copper cladding on top of stone spires. But nevertheless, I think it bears well. It's sort of a scar from this particular environment that Christchurch lives in. Nowadays, that town square, the cathedral square, is vastly different from the original square. If you might have seen the buildings in the background of the first picture I showed you, was largely agrarian and single-story wood frame buildings. Those have all been replaced with mid-sized unreinforced masonry buildings and mid-rise modern buildings, which is really the focus of my discussion today. But first, a little summary about the types of unreinforced masonry and how these are exhibited in this particular earthquake. I'll start out with chimneys, which is the most common. Over 14,000 chimneys were reported seriously damaged or collapsed in this event. And you can see the ghost of this chimney on this painted building over here where I'm moving my cursor. And it fell over this fence and onto the sidewalk. Elsewhere, we saw a lot of examples of attempts to brace chimneys, and in many cases, they were successful, particularly if the structure to which you're bracing the chimney back to is relatively stiff compared to the stiffness of the chimney. That's not always the case, so chimney bracing is not necessarily the sole solution. Another type of unreinforced masonry is fire separation walls, where wood buildings were originally abutting property lines, and they decided, because of the fear of fire spread, they would install these brick buildings. So yet again, another side effect of trying to address one hazard and creating yet another hazard. The problem is these brick walls are relatively stiff. The wood buildings move large amounts in relation to the brick walls, and they can topple over. And you can see this, the rear end of this red wall here, painted for convenience so that we can see that, and also this side wall here, has also been severely damaged due to the differential movement between the brick wall and the wood frame building. The third type of unreinforced masonry are cavity walls. This is where you have two layers or withes of wall separated by a void space. Often between the void space there's a wire tie, and they look like this. Unfortunately, though, when the cracks open up at the mortar joints, those wire ties are largely ineffective, and you end up with a relatively slender set of stacked brick, and it's highly unstable. So this is a very, very vulnerable type of construction, quite prevalent beyond the central business district in the more mundane single-story mom-and-pop dairies and 7-Eleven type stores at the street corners of neighborhoods. The most common type of unreinforced masonry buildings are these multi-wythe walls, and just this is an example of the layup. We have actually buildings of this type as well in California, and you can see that the mortar quality is quite questionable. The joints are often not fully buttered. Many of the joints are actually absent. The collar joints in some cases have no mortar at all. And the adhesion between the brick and the mortar can often be quite low. And the mortar itself can be brittle. So this is what we're dealing with in terms of attempting to install anchors into this type of system or repointing the mortar to enhance its strength. So how do these types of buildings fail? Well, typically the tops of walls begin to propagate off, fall off, and work their way down, so the upper walls also fall off. In some cases, you have buildings that start to collapse from the ends of the building and work their way towards the middle, and in other cases where you have large diaphragms, the propagation can occur in the middle of the diaphragm and work out towards the ends of the building. Many buildings that suffered catastrophic collapses had wall systems that were just really not adequately attached to the roofs and floors. And so what happens there is that they fall outwards onto the sidewalk, through the awnings, and onto the pavement. We have now the ability to capture within a few minutes. These pictures actually were things I was taking off within about an hour after the earthquake. This one, perhaps not, it's a little later, but the next one I'll show you. The left pictures are taken from Twitter, from cell phone users, thanks to the cell phone system being up in Christchurch. And then we can quickly compare those with the before pictures from Google Maps. And this is probably a much earlier, probably one of the first pictures that was taken. The before picture from Google Maps and the after picture from TwitPics. Let me move on from and try to summarize the other types of unreinforced masonry that commonly exist in Christchurch. Stone buildings, many of them monumental, religious or institutional buildings existed, and if they weren't retrofitted, they did quite often suffer very severe damage. And clearly this could be potentially quite life-threatening had there been people around the perimeter of these buildings at the time of the earthquake. And fortunately, the earthquake occurred at such an early time in the morning, 4:35 in the morning, that surprisingly no one was killed in this earthquake. So we have a lot to be thankful for in that respect. Only the taller buildings exhibited in-plane cracking, X-cracking such as this. And perhaps it's due to the short duration. This is the first time I've heard that sort of evaluation being stated. We should look into this further. We actually saw relatively few in-plane cracks in short unreinforced masonry buildings, but 2 of the 7-story taller unreinforced masonry buildings both had X-cracks, one of which had a concrete frame with URM infills, and this one happens to be a perimeter wall system that's, for the large part, bearing wall unreinforced masonry without a frame. Another type of unreinforced masonry walls common in Christchurch are gable walls. These have pointed rooftops, sloped tops of the walls. They're quite common to hide the sloped roof framing behind them, but they pose a real challenge for engineers to try to brace. And many of these walls had been previously retrofitted. You can see the through bolts from prior retrofits. However, in some cases, those bolts are a little bit too low to really keep the upper portion of the walls from falling off. The building on the right-hand side here is the former women's high school, and it was built in 1881 and had been altered at least 5 times since then, as recently as 1962. And so it begs the question, we actually couldn't see any evidence of seismic retrofits that occurred, so this would be a good case study to go back and find out why, as we had many opportunities to address the risks in this building, perhaps in hindsight, it could be a lesson to learn. The triptych along the bottom is from a church that was, we believe, built in the early 1960s, and even then they had some challenges in bracing gable walls back to the roof. There was only one fire following the restoration of electricity. well after the earthquake, I think late in the afternoon on the first day. And I'll mention that there were very substantial indirect impacts from collapsed unreinforced masonry buildings. A lot of modern buildings nearby in the same neighborhood, faced with closed streets, sidewalks that couldn't be walked on, even though the buildings themselves were relatively undamaged. And to give you some broader perspective of that, here's a safety assessment map of downtown Christchurch. So the central business district is once again, if you follow my cursor, it's this area. And for the most part, nearly all the buildings downtown are predominantly green tagged. Relatively few buildings in the downtown area and along the major corridors are red tagged. So in fact, we're dealing with a small minority of vulnerable buildings. And yet there is a substantial amount of severe damage and potential loss of life had this earthquake occurred at another time of day. Over 2/3 of the unreinforced masonry building had damage ratios less than 10% of their replacement value. And only about 125 URM buildings were red tagged. This is data that we're getting from Christchurch City Council and through the University of Auckland. So they've been enormously valuable in sharing a lot of the information that's emerging from this earthquake. So there's another way of attempting to get your arms around the overall performance. Rather than just focusing on the buildings that did poorly, what about all the rest of the buildings? One technique is being developed by the Structural Engineers Association of California, and it's called the Earthquake Performance Evaluation Program, where you take a pod of buildings around within close vicinity to a ground motion recording station. It's that triangle we believe here, although I think it's moved since this. And what you try to do is within a certain radius, examine the performance of all those buildings and see how well they did. In this case, we found that about 3/4 of the buildings were wood frame construction, and the building ages ranged from 1890 to the present. There were some very recently constructed buildings in 2010. 92% of the buildings had no visible damage from the sidewalk. 82% of them had no visible non-structural damage. Now moving on to efforts to retrofit buildings. We saw a lot of efforts to retrofit gable walls, some not so successful like the one on the left, although clearly whatever prior efforts were done, like the presence of these through bolts, did probably make a substantial difference. The retrofit on the right involved a steel bracket that extended up to grab onto the finial at the top of this parapet, at the top of this gable, and it actually performed quite well. Elsewhere in the central business district, there was evidence of parapet bracing, but curiously, not all the buildings and not all sides of every building were braced for parapets. Like in this case, the left side parapet was braced on the main street, but it appeared that the parapet on the right side, the side street, was not. So I think we can go back and find out why that was the case. Perhaps there was funding or other reasons for some of this partial work that's been done over the years. As a result of a 1968 law passed at the national level, there was a trend in the 1970s and the early 1980s called earthquake architecture, where a lot of structural engineers and architects attempted to express the retrofits along the outsides of the building. In this case, they literally wrapped this building with horizontal bands of steel and through-bolted those bands into the building. Pretty brutal from a nowadays architectural standpoint, but nevertheless thought to express what was important to do for safety's sake back in the 70s. And this has since, of course, fallen out of failure. Here's another example of that same sort of earthquake architecture where they used steel rods mounted on brackets on the outside of the building, both horizontal rods and vertical rods. And in this case, the two-story main building did fine. The tower that extended up above the gable wall suffered severe damage, and it's a little unclear as to whether or not the retrofit in fact extended up above the roof line. More recently, we see a lot of evidence of less intrusive retrofits, such as this one that was performed much more recently using fiber-reinforced polymers. There are other types of retrofits that would prove to be interesting case studies, like the building out at Lincoln University You'll note the ground motion in this case was substantially higher than the Christchurch Central Business District. And from general appearances, it appears that the building, parts of the building at least, probably had entire structural systems replaced in order to brace these historic walls on the front of the building. This crane beyond is doing the work on this building right next door, which was unretrofitted. So we have some very good stark contrast between the good performance of retrofitted buildings with similar buildings right nearby that performed quite poorly. Also trickling in, just last week we're beginning to receive additional information from our colleagues in New Zealand, and we're very thankful for that. And we're realizing that there are actually very recently completed retrofits, these done as recently over the last 8 or 9 years. And for the most part, the damage was either none or minor, with perhaps one exception. This building in the lower middle here has what I'll call major damage, and has a 4-inch offset between the walls and the roof. But for most of the rest of the part, there's a lot of minor cracking in these retrofitted buildings. They relied mostly on steel moment frame for vertical elements of the lateral force resisting system, or in some cases concrete moment frames and steel brace frames. Now I'm going to mention a few things about New Zealand's latest policies on earthquake-prone buildings, because I think we have a lot to learn about what they are doing and to compare their practices with those here in the United States. I characterize this as a very comprehensive, well thought out and organized system that extends from products and information that can be used by risk managers, building owners, and policymakers to make decisions. They use the same red, yellow, green system as we have for tagging buildings. Red buildings being unsafe, and we really need to retrofit them either into yellow or green. And there's, consistent with that, initial evaluation procedures that are available that engineers can use to express this in greater detail, as well as detailed seismic evaluation and retrofit practices that go along with it, both force-based and displacement-based. And so, in essence, New Zealand does have an integrated system, and in fair criticism of our situation in the United States, we don't really have that right now. So I think there is really a lot to learn from the way the New Zealanders are in fact managing their risk. Part of this law requires all local governments to adopt a policy on earthquake-prone buildings. Prior to the earthquake, Christchurch had adopted a passive policy that is triggering retrofits upon significant alterations before the earthquake. And now 6 days after the earthquake, they expanded its policy to include mandatory 15 to 30-year milestones for seismic evaluations. They call them, I think, assessments, and if warranted, seismic retrofits over that time frame, or demolitions. So I'll try to summarize the issues associated with URM buildings. What we're seeing are the cumulative impacts of a passive retrofit policy, where there were major alterations to existing buildings. The local government actually required retrofits. But many of the mom and pop owned, small business owned buildings have not been retrofitted, and that's quite obvious. And they're probably some of the most vulnerable buildings. And so you have this unevenness where a lot of the grand institutional buildings, or the ones owned by major corporations, have in fact been retrofitted, at least a few of them, and there's still movement in that direction. And yet the vast majority of the remaining buildings have not been systematically addressed. And this is really an outgrowth of this passive retrofit policy. As a result, there's a large number of partial retrofits throughout the Central Business District and elsewhere, as well as a few systematic retrofits. And we can learn from both of those. And perhaps we'll find that partial retrofits are in many cases doing a tremendously good job. It's still very much too early to tell how effective those retrofits are, but it appears to be rather promising. I think that documentation of the performance of these retrofits is really going to be critical, not just to New Zealand, but to the western part of the US and Canada, particularly for regions of moderate seismicity, because they're not using the same levels of design criteria we would here, for example, in the Bay Area. Performance unfortunately, is going to be somewhat inconclusive because of the moderate levels of ground motions, particularly in the range of short period vibrations and maybe duration. And yet, many buildings appeared to be right on the verge of collapse. So we know that based upon their performance, it could have been much worse had there been a few more seconds of ground motion. So we should be expecting much more damage and casualties, particularly if an earthquake of this type would have happened at another time of day. Now I'm going to shift to modern buildings. I just have I think 3 modern buildings to describe and a little bit about the port, and then I'm done. The Westpac building was a 14-story structure built in the early 1980s. It has a center core around its elevators of concrete shear walls with diagonally reinforced coupling beams, and yet the perimeter concrete columns had spalled during the earthquake. So the owner was required to go up and scrape all of the loose cover off the columns, and this is what remains. While it's a little bit disturbing, they've allowed the building to be reopened, and they've allowed the public to continue to use the sidewalks below. The Women's Hospital at the Christchurch Hospital campus is the only seismically isolated building on the South Island. It's a 9-story building with a perimeter concrete moment frame, and there are 2 bays of steel concentric braces that go up part of the height of the building in the transverse direction. There is a moat around the perimeter of the building that was designed with an 18-inch gap. The design ground motion, the design response motion for the building above the isolation level was 16.5 inches. And just for comparison, we think that the amount of motion that actually occurred in this earthquake was about 3 inches. And it varies depending upon where you are in the structure. There were 2 types of isolation devices, one pot bearings and then lead rubber bearings. And you'll notice that some of the lead rubber bearings, like in this case, had a permanent residual displacement on the order of 1 inch. And this is in relation to a total motion of 3 or so inches. And so it's rather interesting to see this much permanent displacement. I'm sure there's going to be a lot of studies on why this building performed this way. There was some cosmetic non-structural damage at the structural separations, and yet what we've been told is that the non-structural performance, the functions, the loss and the cracking and so forth that did occur was very small in comparison to similar sized buildings elsewhere on the campus that were not isolated. The third building I'll mention is a 2 to 3 story precast concrete parking structure. It relied on a steel eccentric braced frame, which we believe is probably not something you would see, or even it's not allowed in the United States. But nevertheless, it's an interesting structure for several reasons. It's pretty rare that we get an opportunity to actually see how EBFs perform in earthquakes, and here's a good example of that. So you have precast concrete beams and columns, and then there is a steel beam with an eccentric brace connection in the middle. You'll notice that the braces don't come up and meet right at the center. There's an offset, and this panel joint in the middle is designed to shear and absorb a lot of energy during the earthquake. Hence, that's why it's called an eccentric brace frame. And that panel actually did its work. You'll see that the paint flaked off of the panel zone. And yet, it did result in a lot of drift throughout the building, so much so that there were a series of columns at the upper levels that suffered severe damage, spalling and X-cracking of these precast columns. So I'm not sure we can necessarily call this what we would expect, because the ground motion, frankly, was a lot lower than what was designed. And so there's going to be a lot of investigations of this particular building. It didn't collapse, so in that sense it met a performance objective, but I'm sure the owner is not quite happy at this point. The Port of Lyttleton is my last subject, and this is an aerial view. I think you've heard already some snippets. Obviously, we didn't coordinate so much, but I think our statements are somewhat complementary. The port has a nice variety of shipping facilities. It's kind of a full range of shipping facilities. On the right here is a bulk coal export facility, and I think you heard a little mention of that before, and I'll show you some pictures of that. In this area, there's a containerized cargo facility, and then over here you've got petroleum and other oil products, and then they use these piers for shipping livestock and other things that don't fit into containers. So they really have quite a nice variety. There's different age vintages of facilities, and in fact the part of the oil petroleum wharf has actually been seismically retrofitted. So there's going to be really a nice test bed of information that comes out of the performance of this port. We estimated at the time that we were there that there was about 8 inches of vertical differential settlement in various places. We weren't quite sure how much lateral spreading had occurred, but it was obviously quite extensive, and it took place over several dozens of feet, so it's rather hard to estimate that. And I'm sure that they're going to be doing surveys. But so you can anticipate there's both differential settlement as well as lateral spreading that occurred. And there are some impacts, adverse impacts associated with that. The most notable one is in this coal conveyor. So they convey coal up this conveyor belt and put it into the ships, basically. And the left side is basically anchored closer to the land, and the right side is anchored further out towards the sea, and of course they spread apart. And what happened was that the one end of the conveyor lost its support, and so they had to come back and add this little bracket after the fact. The unpainted portion of this was added after the fact to extend the bearing out and accommodate the differential displacement that occurred. The crane rails were not seriously damaged, and therefore the cranes were still operable, unlike many other earthquakes we've seen around the world. And so the level of disruption from this particular event was really quite minor, probably on the order of, we've been told, 26 hours. At the time that we were there, the estimates in costs were 50 million New Zealand dollars, and now we hear it's up to 100 to 200 million. That gives you a sense of their uncertainty over time. Our numbers were about a month ago now. Let's see. I want to give credits to a number of people who provided images for me. And look, just let me close by reflecting once again back on that cathedral spire, which I find quite fascinating. And I think it says a lot of things about Christchurch, and maybe it's something we should be reflecting on as well. It suggests there's actually been a lot of progress made in Christchurch, particularly on institutional buildings. And I think they have a real challenge ahead of them because the past has been focusing on retrofitting buildings that are of monumental importance to the community, but they haven't in the past been really reflecting on the more mundane buildings, the mom and pop stores, the small businesses. And I do think that the challenge they have in front of them, and they've set out that challenge, is over the next 30 years they actually want to do that. So the question remains, can Christchurch really shift their gears and find affordable ways to repair damaged buildings or replace them or retrofit them? And that's in the near term, but in the long term, they're also going to have to find financing to do seismic evaluations and retrofits on perhaps thousands of buildings. They have laid out earthquake-prone buildings as not just including unreinforced masonry, but other building types as well. So it will be an interesting effort to watch from a distance and to learn as well. And I think we actually have a lot in common with New Zealand. And in that sense, it's an area of the world that we really need to maintain close contacts and learn a great deal from. Thank you.